Okay, I wanted to talk a bit about heat at the mid-ocean ridge. So you can see on the screen here, MOR stands for mid-ocean ridge. So we've seen in the previous PowerPoints that a lot of the heat comes from the oceans, and that's because of this mid-ocean ridge. So let's look at what's going on at the mid-ocean ridge. So you might have seen this diagram already in your notes. So this dappled area here is your crust, it's your thin crust. This white area here is actually your upper mantle, and together they form the lithosphere. Remember, this is this firm layer on top of this mushy asthenosphere, and because you've got this firm layer on top of the softer layer, that's why we have plate tectonics. That's why this firmer layer is able to move around. And so underneath here, this dappled area is your asthenosphere, which is also part of the upper mantle. And so what you have here at your mid-ocean ridge is you have hot material, in the mantle rising up. And so hot material is less dense, so it's rising. You can think of your kettle. At the base of the kettle, you've got your element heating up your water. The hot air rises to the top. And so that's what we've got here. We've got this hot material rising. And we have something called partial melting, or it's also called decompression melting. And so what that means is as this material is rising up, it's under less pressure, and so what happens is the temperature at which this material in the asthenosphere melts, the temperature at which it turns malt to liquid, or melts, is lowered. Because there's less pressure, it will melt at a lower temperature, and so you get these little blobs of melt inside of this asthenospheric mantle. And so these little blobs of melt grow and grow and grow, and they coalesce with each other until you've finally got a large amount of melt up here, and you've got this magma chamber. And so this is going on here below the ridge. And you can see the asthenosphere is very thin below the mid-ocean ridge over here. And the lithosphere also thins because the asthenosphere is actually coming to the surface here at the mid-ocean ridge. You've got this magma coming up, this partial melt erupting at the Earth's surface. In this area here. And so what does this ridge look like when you zoom in? And this is what it first looks like. So when a ridge first forms, it's actually not below the ocean. It's somewhere on the continents. And so you can think of this example as the East African Rift Valley. So up towards Tanzania and Kenya and Ethiopia, the crust there is splitting apart. And you can see this arrows of magma coming to the surface. You've got these fault valleys, you've got volcanoes forming along here. And eventually it'll split apart far enough, you can see it's these gray areas here, that new basaltic crust forms at the ridge. And so this is when it turns into a mid-ocean ridge that's below the ocean. And you've actually got new oceanic crust forming here, and you've got a new ocean basin. This becomes wider and wider. And so you can see eventually you've got this large ocean between these two continents, and that's kind of what we've got today between Africa and South America. So it would have started off with the continents together. You can think of Gondwana being together here, the African plate being right next to South America, and then over time this oceanic crust opened up. And so now we're going to look at what is actually causing heating at the mid-ocean ridge. So we've already spoken about the fact you've got magma coming up. And sorry, I forgot to mention here, in my mind when I learned it in school, I kind of pictured this big body of magma sitting at the ridge. And it's not really, it's below the surface. Even here, it's below the surface, and you've got cracks in the crust. And this magma is coming up through these cracks. So it's not that you just got this pool of this like lava pool in the ocean, below the oceans. You've actually got crust, and it's coming up through cracks as dikes and different rock formations. And so what else is causing heat release at these ridges? It's something called, you can see on the right hand side here, hydrothermal circulation. And so what this means is you've actually got this layer here is the blue oceanic surface. You've got ocean water going down into this basaltic crust that is just being created at the seafloor. So that's what this brown checkered rock is down here. This is fractured basaltic rock. So it formed at the mid-ocean ridge, it cooled and it moved away, but it's actually still quite hot. It hasn't cooled down to the point of being the same temperature as the ocean. And so what happens is it fractures because it's coming into contact with this cold ocean water. And so it's got these fractures which then help this water move through the rock. This water moving through the rock gets heated, and then it comes back up to the surface. And it may look in this diagram like it calmly comes back to the surface, but often it comes up as these smokers, these black smokers, which I can show you a video of now. They're also white smokers. And so this, there's very thin sediments at this point. So this is young crust that's just been created. It hasn't been covered by sediments. So this water can circulate well. And ultimately, this circulating water is helping heat be released at the ridge. And you can see this is young oceanic crust that's just formed. What happens as we move further away from the ridge and we get old crust? Well, it's cooled down a bit. It's got a bit more sediment on top of it. It's still got fractures, but the water can't really get through these sediments to move through the fractures, and there's not much heat anyway to remove. So there's really a lot less heat coming out here. And so hydrothermal circulation is another way that heat is being released, but it's actually quite a hard way to measure. It's quite hard to measure how much heat is being released here. And you'll see in the plots that we look at now how this is evident. And so this is to show you how heat changes as we move away from the ridge. So 0 here means when the ocean is 0 years old. And so this is obviously at the ridge where this new material is being formed. So you can think this is your ridge on the left-hand side. And as we move away from the ridge towards the right, you can see we're getting to 180 million years old, and that's the oldest ocean. And you can see the heat goes from 50, 100, 150 megawatts per meter squared. It's highest at the ridge, obviously, that's where the magma is coming out, and it's going down as you move away. And you may ask, what is the difference between these dots and this curve? From what I understand, this curve is what they predict the heat flow to look like, but these data is what's actually being measured in the ocean. And if I remember correctly, the reason why these dots are a lot lower than what's predicted is because, like I said, it's quite hard to estimate how much heat is being lost by something like hydrothermal circulation. So it's quite easy to remember this. You're close to the ridge, the heat is high. As you move away, the heat is going down. So if I'm at the ridge and I'm moving towards, for example, the right-hand side, it's going down. The plot would look exactly the same if I was at the ridge and moving towards the left-hand side, because it's hottest in the middle and it cools away from the ridge. So this might confuse you because you're only seeing kind of one side of the ridge. This is a similar plot, but this is looking at depth. And so what this is showing us is actually we are below the ocean at the mid-ocean ridge, for example, like the mid-Atlantic ridge, but at the ridge, the elevation is actually highest. It is a ridge. It's got a higher elevation than the surrounding ocean floor, which is these dots here. So you've got a higher elevation here, and then the elevation decreases away. So a plot I don't have, but I would still like to talk about, is, and it links to both of these plots, is that if your temperature is highest at the ridge, it also means your rock is the hottest, and therefore it's the least dense. But as the rock cools, moving away from the ridge, the density is going to increase. And so obviously then your plot is going to be opposite. You're going to have a low density close to the ridge, and the density is going to increase away from the ridge. And this is a very important thing to remember, because as the seafloor is moving away from the ridge, their density is increasing. This helps drive subduction. So we're looking here at a ridge, but further off to the side here, you've got subduction happening. And this is all linked to the fact that you've got more dense rocks here. They kind of, you can think of the density, because it's high, is helping it slip into the subduction zone. You can think of it that way. So even though this is what your heat flow and your elevation plot look like when it's high at the ridge and decreases going away, your density is opposite. You've got low density at the ridge and it increases away towards subduction zones, and this density difference helps drive plate tectonics.